For the second part of the tutorial, let's consider the JM representation of states. Any particle that has an intrinsic spin can be represented in terms of the JM representation, where J is the total spin of the particle and M is the Z projection. So for example, if we wanted to represent the spin 1/2 Z plus state in terms of a JM ket, we would write ket and we would give it a list here that consists of the J and the M value, so that would be 1/2 and 1/2. And if it were the Z minus state, that would be then given by 1/2 and a minus 1/2 in the right slot. We can take the dagger of the ket K and turn this into a bra, and then we can take the inner product or the bracket B dot K. And the JM representation states are also orthonormal. There are convenience functions for creating top and bottom states for when we look at tensor products later. One of the functions is JM top, so it will create a top state. So 3/2, for example, spin 3/2 is 3/2, 3/2. And a JM bottom state with spin 1 would be 1 and minus 1. Now the operators, the spin operators that we use to operate on JM representation kets, these start with J instead of S, because the S operators that we defined in the first tutorial, part 1, those have matrix representations, whereas the J operate on kets that don't have a matrix representation, and those would be these JM kets. So for example, if we take JZ operating on this ket that we defined as K, so the 1/2, 1/2, it will give us H bar over 2 times the same ket. And if we want to operate with the J plus operator on the state 1/2, 1/2, we'll get 0 because we're on the top of the rung. But if we operate with J minus on that ket, it will lower the M value by 1, so it goes from plus 1/2 to minus 1/2. So if we just input an arbitrary JM ket in terms of J and M, then if we operate with JZ on that ket, we pull out the M, H bar, and if we operate with J plus or J minus, we get the expected general formula for those. Now, I mentioned tensor products, so it's of interest to solve problems with more than one particle. And in fact, if you have interacting spins, you need to address this through tensor product states of particles. So in the QM package, tensor product states are instantiated as follows. So you use the TP ket, which means tensor product ket. There's a 1 in the first slot. You don't have to instantiate it with a 1. You can give it any number here. This is just the common factor that will be in front of both of the kets. And then you have your two kets. So here I'm instantiating it with 2 spin 1/2 particles, both in the up state. And if we want to take the dagger to create the bra, then because we're working with tensor product states, there's a special tensor product dagger. So we would take the TP dagger of this ket K, and that gives us the TP bra. And you can see that in slots 2 and 3 here, we have bras. Then we have operators that operate on tensor product states, and these are the operators that have a T in them. So this is J total Z. So J total Z operating on the state ket K we'll bring out an h bar as the common factor because it's the total z, so we get half from the first particle and plus half from the second particle. And those go into the common factor slot for the tensor product ket. And there are other operators that operate on these two particle states. So for example, we have J1 plus and 2 minus, so it would try to raise the m value of the first ket, and it would try to lower the m value of the second ket. Now, this particular ket has, we're at the top rung of the ladder here, so when we try to operate with J1 plus on the first ket, it will kill the ket and give us 0. So there are other tensor product operators, and I'll cover those in the part 3 video.